Okay, so after doing the Chapter 1 test, and really Chapter 1 is just a review of everything last year, we're going to get into the main goal of this, which leads directly into calculus. Chapter 2, Understanding Rates of Change. Okay, let's look at a line. Let's look at this line. You should be able to immediately at this stage tell me the slope of this line is 3, which means if I go up, let's take these points here as a great example, this point there and that point there. Notice the y-intercept is right over here as well. Okay, and let's jump right to a drawing. Slope of 3 simply means 3 over 1, which means the y goes up 3. Since it's positive, y goes up positive 3 as x goes up positive 1. That's why they're both positive. And if you look at that, that means you could draw here 1, 2, 3y, 1x rather, and end up at the next point. And you could do this over and over and over and end up at the next point. Or you can go backwards, down 3, left 1, and end up at the next point. And that is the slope of this line. It is always 3 over 1, but we just write 3. Whatever those units are, it could be whatever. If this was a car, it could be going 3 kilometers, which would be along the y-axis, and the x-axis would be 1 hour. Obviously, that's pretty slow for a car, so let's call it a person walking. And this measures what's called rate of change. Now, the thing about a line is its rate of change anywhere in this line is always going to be 3. It's always going to be going 3 up, 1 over, 3 up, 1 over. And if you go backwards, you do the opposite. 1 to the left, 3 down. If you have to go backwards, down 1. All graphs are read from left to right on the x-axis, so backwards is this direction. So it's always going to be 3. That means the rate of change on this line is measured by the slope. And we're going to have to learn lines and remember what lines, how to find the slope, even when it's in different format, because it's very important. And you might say, well, that's information I already knew. You didn't really help me. Let's take another line, but not a line. Let's take a parabola. Let's take x squared, and we're going to lower this parabola by 2. And we're going to get rid of the line. Well, the rate of change of this parabola isn't like a line. Here it's going down, down, down. So if I were to draw a slope, and I might as well take some key points here. If I was to draw this one in the same way as this one, you can see I can't really draw a straight line through it. It doesn't really work. So noticing that it's negative slope here, it's almost like a line that goes down in this direction, right, like that. But then when it reaches its vertex and turns around, it's a line that's going up like that, right, in that direction. So on this side of the parabola, the slope is clearly negative. It's going down. And on this side of the parabola, the slope is clearly positive. And it's also possible to see that the slope, as I round the corner here, let's look at a line like this. As I round the corner here, the slope right there of that part of the vertex is less steep than the slope, let's say, if I was up here, I can see a line almost right in it. Right there, it's more steep, and you might say, oh, that's right on the line, but if you zoom in, you'll see it's not. Which means not only does the slope go from negative to positive, but it's very steep here. Let's say it's -9 here. When we round this corner, it's only about a -2. And guess what? When we hit the vertex, the slope right at the vertex is 0 because we have a flat line as it turns around. Then suddenly it's becoming a slope of 2, a slope of 3, a slope of 4, all positive, a slope of +12. As we get really steep, the slope keeps changing. Well, how do you measure rate of change for a parabola? And you might say, why do I want to measure rate of change? What does this lead to? Rate of change is measured a lot in science. It can be how quickly a chemical reaction happens. It could be, will the chemical reaction happen in a certain situation? It can be studies of mechanics, engineering, computers, finance. Rate of change touches almost every branch of science. And it's a key important thing to be able to predict and say, let's say you're a financial analyst and someone says, will the stock go down? You have to read all the indicators to be able to provide sound advice, otherwise you're just a guy guessing about what's going to happen in the future. And if you're successful in your predictions, you're going to be a successful person. People are going to hire you. So that's just looking at the finances. Engineering, you want to be able to say, will this bridge hold this weight? And if you're wrong, people die and you will never work again. So all these things might seem insignificant at the level, but they feed into a lot of different sciences in a lot of different ways. If you don't understand what's going on in your data, you can't predict anything. So that's first rule. Now in that second rule, you might say, well, how am I going to measure the rate of change? Well, one way to do it is to draw a straight line from one dot on the graph to the next dot. And we can look at that red line that I've just drawn, and we know that lines, it's easy to find the rate of change of a line. It is just the slope of that line. And since we're drawing through those 2 points, and one way to look at it is drawing it right through the 2 points. So let's say it's there, and then I'm just going to move it a bit. There we go. And you can look at that line more like that. It's very easy now if I find a pure point on this line, and I don't know if I can. There's a pure point there. That's at -2, 1. And I know this pure point here is 0, -2. If I take that slope, -2, -1, I get -3 for my delta y. 0, -2, I get +2 for my delta x. And I get a slope of -3/2, which is -1.5, which means between this point and this point, I get a general idea of how that rate of change happens in that drawing. And that's called average rate of change, because I've taken it over an average of 2 different points. That's what the delta is. It's an average over 2 different points. And I've come up with a general conclusion, but I want you to notice something. While that red line is fairly good, if I were to take it between this point way up here and the vertex, and then draw a line between the two, you can see that clearly the slope is different, isn't it? And so clearly the slope between these 2 average points is different than the other 2 average points, which means I'm losing accuracy of what's going on in this graph. You can see the big gap here between the red line and the actual blue line, and the blue line is what we're studying. So when I'm taking a great big picture like this, I'm not getting much accuracy. You see this a lot in weather. In other words, if this is Tuesday, it's much easier, if this is Tuesday, it's much easier for me to see what's going to happen Wednesday and Thursday and Friday than it is to predict what's going to happen next week. And while that's a simplistic way of saying it, it's saying that the changes are so dramatic that measuring it over too much time is useless. For instance, if I measure from this point to this point, my conclusion to you is, oh, the slope is 0. But is that really what's going on between this point and this point? No, the slope is negative, 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 turns around, positive, positive, positive. But if somebody only told me those 2 points exist on the graph, I'd think we're dealing with a straight line, horizontal line. So you can see that if I draw this line between 2 points that are far away, I get an idea of what's happening, but sometimes I don't get the best idea if I get the wrong points. But as I draw the line between 2 points that are closer and closer, I want you to watch what happens. And here I'll just draw the line straight through. And then finally I'll draw a line very close to the vertex. And you can see, and let's just say I don't want to study the vertex because the vertex is going to be flat. But you can see as I get closer and closer between 2 points, between this point and this point and this point and this point, I'm very much touching the blue line. Let's look at a point between this point here and the vertex. So if I draw a line, am I pretty much touching the blue line? Yeah, I am. I'm getting much more accurate look at what's going on the blue line with my new red line. My red line pretty much overlaps the blue line. And that's what I'm trying to do. I'm trying to get a good idea of what is actually happening with the blue line. And eventually what we're going to learn is how to take the slope at the specific point, and just that one point, what we're trying to do is draw a line, red line, that's exactly perpendicular to the point here, and that's called a tangent. And the distance between 2 points, where it's an average change, is called a secant. When you draw a straight line between 2 points, it's called a secant. When I'm trying to draw a line at exactly the point, that's called a tangent. So if I do this line, I'm pretty much getting an idea of what's happening at the exact rate of change at that one line. And you can see it when I zoom out a bit. See, I'm getting a good idea of that red line here, exactly what's happening at that dot. And that is called a tangent line. That's a line that I've placed perpendicular 90 degrees to that dot as best I can. And the other line, and this tangent line, it measures the instantaneous rate of change. So that tangent line measures instantaneous rate of change, which means exactly how fast the slope is at that specific dot. Whereas this line between the two dots measures average rate of change. And that's the two terms you're going to have to get used to. And that's all going to be all of calculus and all of functions and how to measure it. So obviously when I'm measuring average rate of change, a secant, I'm going to need 2 points on the graph. Then I'm going to draw a straight line. Then I'm going to find the slope of that graph. And the slope is going to be equal to the average rate of change between those 2 points. If I'm trying to find instantaneous rate of change, instead I'm going to draw let's draw it on the other side. I'm going to try to draw exactly perpendicular. Let's use it right here, right there. And let's draw our line purple. Or blue. Now, green, even better. So let's say I was trying to find exactly at this point here, and I drew pretty much a line that is 90 degrees to that point. And that is called a tangent, and I need to find the line, the slope of that line, to judge the exact rate of change, the exact slope at that point. And you can see that when I'm drawing the tangent, it's a lot of guesswork, whereas I'm drawing the secant, I'm working with 2 exact dots. Now here's the other secret. Let's say this line here is trying to measure, I'm trying to get the instant rate of change of here, but I'm starting by taking the average rate of change here. Well, as I move the 2 dots closer and closer, I'm going to get an accurate idea, closer and closer, and keep taking the average rate of change between those 2 dots, closer and closer. As I get those dots closer and closer to my target, my average rate of change is going to approach what? It's going to approach my instantaneous rate of change. So eventually they're going to become the same. That's also the goal of calculus, is to learn how to do average rate of change and then get closer and closer to the dot so that you get a good idea of the instantaneous rate of change. And simply because at this stage, taking a line and drawing it through here is tough to guess. But the dots are very accurate. They fall right on the graph. So that's what we're going to be doing. And the other thing to realize is this leads into calculus, and calculus eventually is going to help you take the original formula. So here's the original formula. And calculus is going to help you, and I'm going to jump straight to calculus here. It's going to help you come up with a formula that's called the derivative. And the derivative comes from this formula, and it will help you figure out the slope at any one point on the line. The derivative of this is that, and I'm going to let you in on a little secret. What you do is you find all the x's that have an exponent. How many x's do we have as an exponent? Just that one. Is there any x here? No, so we can ignore that number. You're going to take the number and lower it down in front, 2, and then you're going to reduce that number by 1, 2x squared. This is going to be the slope, the formula for the slope at any point on this graph, so it's just going to be 2x, which means if I'm at x 2 right here, right there, you can kind of see that this point, if I put it into this formula, is 2, 2. The slope of that graph is going to be this formula. So if I take my 2 and put it into this formula, I'm going to discover that slope there is 4. And as we do it algebraically, which is what functions is trying to teach you, you're going to discover it's reaching what we end up learning in calculus. Now the reason I tell you this is so that you can see the connection. You don't need to memorize this part of it, but if you learn this now, you'll have a much better idea of what's coming up in your next course. So I would urge you to learn some simple basics of calculus at this stage, but not necessary. Let's look at a couple other formulas. Suppose I'm dealing with the line cubic, y is equal to x cubed. What would its formula for its derivative be? So we mark a derivative like this, y prime. I only have one term in here, it's x cubed. So I know I'm going to lower the 3 in front, 3, and I'm going to lower the exponent by 2 squared. This is now the derivative of this line, and any x value, 3x squared, I can now plug in the x value. So when x is 2, let's say, 2 squared is 4 times 3 is 12. I can tell you the slope at that point will be 12. Now I don't want to bog you down with that, but it helps to understand where we're going. And so if you want more information on calculus, let me know. What if it had more terms in it? Well, if it has a term that's not got x in it, you can ignore it. It's still 3x squared. But if it has a term that has an x in it, you would lower the 3 here, and you still get 3x squared. Then you have a plus. And what's the exponent over the x here? It's 1. What happens if I lower that in front of the 7? Okay, 1 times 7 is 7. I've got to lower this exponent by 1, which is x to the 0. What's x to the 0? It's anything to the 0 is just 1. So this becomes the derivative formula for that. With this formula, I can find the slope anywhere. But that's not what this chapter is teaching. That's next course. The reason I'm spoiling it is so that you can see why we're learning this. So let's continue on and just learn it. Here we go. So first they want you to remember how to find a slope. Yeah, and I'm not going to go through this. You take your delta y, so y minus 3 is 4. And you divide it by your delta x. 5 minus 2 is 3. And 4 divided by 3 is 4 over 3. So the slope of this line is positive 4 over 3. Doesn't matter if it's negative, it'll still work. So I'm going to just really quickly in chicken scratch do some of these. It's all going to be in chicken scratch because this is like grade 11 math. Okay, let's have a look at this. What about this one? What's the y value here? 5. What's the y value here? And I have to subtract minus 1. That's a mistake a lot of people make. The subtraction's always there, and then you put the unit in there. What's the delta? It's minus 4. And you always got to use the delta x that you use here with the delta. See, this delta y has, this x has to match, this x has to match that y. I cannot suddenly put, instead of minus 4, minus 1, which is the, 3, which is the x from over at this one. I have to use the matching x that went with this one. So I get minus 4, and then minus, and what is it? Positive 3. So what's 5 minus minus 1? It's 5 plus 1, it's 6. What's minus 4 minus 3? It's minus 7. We don't leave the minus down there, we just put minus 6 sevenths. So that means this slope of this one is minus 6 over 7, which means it's going down 6 units of y and over positive, because now if we put the minus up here, that's positive 7, over 7 units of to the right, and if we draw the line, that's what that line would look like. This first one had a positive rate of 3 over 2, which means it's going up 3 units of y, and to the right 2 units of x. So it would look like that. That's a slope of 3 over 2. 3 units of y by 2 units of x. And it doesn't really matter where I put this minus. I could say, I can reverse this to go backwards and say I'm going left 7, so minus 7 and positive 6 to get the point behind us. But this minus kind of helps you see where the line's going. You keep the minus sort of on top and plus. Now you might say, well, how come it's not minus 6 and minus 7? Because when we came up with minus 6 over 7, what it's implying is one of them is positive and one of them is negative. What a lot of teachers will do is just put your textbook will just put this minus over here. Then they'll put the fraction right there, and the minus isn't really associated with either one. And that's just sort of saying it's a minus 1 in front of positive 6 and positive 7 over positive 1. So you can attribute this minus 1 to the top, and the bottom stays positive. So you'll see this in your textbook where the minus is not associated with either number, but it simply means one of them is minus, not both of them. If they were both minus, you would have a positive 6 over 7. So they're not both negative. So then it wants you to do the same. Calculate the finite difference. Identify the type of function that's in the table. So the finite difference is the sort of the difference as you go along between each thing. So let's work with one box first. So we can just look at the difference y. So what is this y minus that y? Minus 1 minus 1. The difference is minus 2. What is minus 5 minus minus 1? It's minus 4. So the difference here is minus 4. What is the difference here? Minus 13 minus minus 5 is plus 5, which is minus 8. What is the difference here? Minus 9 minus minus 13 becomes minus, 16. So you can see they're doubling. Minus 4, minus 2, minus 4, minus 8, minus 16. And then the last one I can predict is minus 32. Now you can take their second differences, because this tells me it's not a line. It's not a line. If all those differences were the same, we'd be dealing with a line, but they're not, so it's not a line. So now we're going to go to the next level, which will tell us if it's a parabola. And you look at what's called the second difference. What's minus 4 minus minus 2? It's minus 2. What's minus 8 minus minus 4? It's minus 4. What's minus 16 minus minus 8? It is minus 8. What is minus 32 minus minus 16? It's minus 16. Those are not the same number. So we can see that it's not x squared. And if we continue repeating, we can see that the differences continue. Repeat. See how the numbers are repeating? They're just being pushed over to the same. And that immediately tells me we're not dealing with x squared. We're not dealing with x cubed. We're dealing with a growth function. And since each multiplier is going down by 2, we're dealing with and each difference up here is 1, by the way, 1, 1, 1, 1. We're dealing with a growth curve or a decay curve. And so since it's going down by a multiplier by 2, I know the base is 2. And then if we look, how do we get 2 to the 1 to equal 1? Don't know. But how do we get 2 to the 2 to equal minus 1? So to figure it out, you'd have to, there's ways, and I'm going to get into it later on. But I can tell you right away that that is probably a decay curve. So let's check it out. A half to the power of x. And here is 1, 0, 1. And what happens when x is 0 here? Well, can we go backwards and predict what this number is going to be? It's going to be half of that. It's going to be minus 1, which means when x is 0, this number is going to be going backwards or upwards by 1. So it's going to be 0. So it's going to go through origin. And then as the x's increase, the y's get smaller. So I think what we're actually dealing with is a growth curve that's upside down. And remember, it goes through 0, 0 here. And we're probably raised by 1. Let's see if we got that. We're going to make a table. And we're only going to be concerned with 0, 1, 2, 3, 4, 5. And see if we got the same results as our table. Minus 13 minus 29. Not quite. We're going to have minus 1 minus 5. So it's going down faster. So we probably have some sort of multiplier beside it. This jumps down to minus 5. Let's try minus 4 just in case. No, definitely minus 2. So there's probably a multiplier in front of it, like 2. And there's probably no addition. Yeah, the addition's probably plus 3. So let's see if we got it there. And I'm just guessworking. Minus 13, minus 20. Yeah, we did get it. So you might say, oh my God, how did you come up with it? Well, I knew it was sort of a growth curve, not a decay curve. And I knew it was flipped upside down. I also knew because it jumped by 4, there's a multiplier. Now, there's all sorts of ways. There's a way to mathematically figure this out. But when I did these differences here, it showed me instantly that it was a growth curve by a factor of 2. That's because these are multiplied by 2 over and over again, no matter how many differences I take. So I knew I was dealing with 2 to the x, and since it was going down and not up, I knew that it had to be flipped. After that, it was a lot of guesswork, and I just happened to guess the right one. But since it says identify the type of function, all you have to do is say, well, that's a growth curve, probably flipped upside down. And you might say, I don't think I can figure that out. Well, that's going to come later on. I'll show you more about how to do it. And it's a very important skill to be able to take data and figure out the curve. And it all has to do with the first, second, third, fourth differences. And then I think I have a video on figuring out as well. The first differences in my x here are 1. My differences here, 11. Then 17. Then it looks like it's going to go up by 6 each time. 31, 33. No, a little bit. Oh, sorry, 23. Yeah, they're going up by 6 each time. And then, so 26. Nope. 29. And then 35. Okay, so it's not first differences. Those are not all the same, so it's not a line. Let's look at second differences. It goes up by 6. 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 Great. If I look at this, if this went up by 11 and this went up by 17, which is 6 more, it's safe to say that when x is 0, this is only going to go up by 5. So what's 5 off of 0? It's minus 5. So when x is 0, I can see I'm at minus 5. Now you might say, why is that important to figure out? Because now I know where the y-intercept is, and I know that for all parabolas, since I'm dealing with x squared, and it's clearly going up as y is going up as x is going up, so it's positive. Since I know where the y-intercept is at minus 5, I know I can tag on a minus 5 right here. Then I can even test some numbers. When x is 0, I get minus 5. When x is 1, I do not get 0. Okay? Which means there's probably a 5 in front of this. So when I do 5 times 1 and then subtract 5, I get 0. Let's try with the next one. What's 2 squared times 5, 20, minus 5? No, it's not 11. So you can see that I'm not going to get the right numbers. But let me show you something. It was really important to figure out this number here, because I can definitely tell you there's a minus 5 in there, because when x is 0, this whole thing, whatever's here, is going to become 0, and even if there's a second term, it's going to become 0. So we know that if I put it, if you remember, the standard formula for a parabola is ax squared plus bx plus c. So let's work with this formula. So it's ax squared plus bx plus c. We happen to have figured out that c is minus 5. So right away we know we can replace this c with a minus 5. So I kind of cheated on that. But let's pretend we didn't know what c is. Okay, let's pretend we're only working with this data here. And let's use clean data. Here we go. Well, we happen to have a formula, right? Can we not figure it out when x is equal to 1? We've got x is equal to 1 here, and we know y is equal to 0. So on our first line, we can say, well, let's come up with one formula. Here's our first formula, 0. How many variables are we missing? We're missing a, b, and c. So we need 3 formulas. So when y is 0, x is 1, isn't it? So what's 1 squared? It's 1. So I get a. And what's 1 times b? b plus c is equal to 0. Great, let's come up with a second formula. Let's use when x is 2. Y is what? Y is 11, says from the chart. So that means 11 is equal to a. What's 2 squared? 4. So that means 11 is equal to 4a. What's 4 times b? 4b. And we don't know c, right? We figured it out, c, technically, but we're pretending we didn't. Now let's use another formula. We're going to come up with a third formula. We're going to use when x is 3. We know that y is 28. What's 3 squared? It's 9. So we get 9a. What's 3 times b? 3b. Oh, by the way, this should be a 2b. And plus c. We now have 3 formulas. And now we can figure out the other 2 by manipulating those 3 formulas. And I might as well teach you because this is an incredibly useful skill. If you have the general formula and some data, you can figure it out. So now, let's find a version of c here. C is equal to what? Well, it's equal to 0 minus a minus b. So if c is equal to 0, which is just 0, so it's just essentially c is equal to minus a minus b, that means on the second line I can replace c with those 2 terms. And don't forget, so let's do that. So in the green line, I'm going to replace 4a, 11 is equal to 4a plus 2b, and I'm going to replace c plus minus b, a minus b, which ends up just being minus a minus b. Now I have common terms, so I can rewrite that. What's 4a minus 1a? 3a. What's 2b minus 1b? It's this. So now I can replace this formula here with this. Right? Now I can also rewrite that in terms of b. b is equal to 11 minus 3a. Now I go to my third formula, and I already know that c is equal to minus a minus b, so I can replace that with minus a minus b. Sorry about the time it takes me to do it. There we go. But now I can replace this b right here with the formula I have right there. So I'm going to rewrite this now. 28 is equal to 9a. And instead of plus 3 times b, it's going to be 3 times 11 minus 3a. And then it's minus a again. And then instead of minus b, I'm going to replace in brackets 11 minus 3a. So I've essentially replaced b everywhere I see it with my green formula for b. This becomes 28 is equal to 9a, and then I'm going to distribute this bracket. Minus a, and then I got to distribute this minus 1 through this bracket. Now I can group all my a terms. I get 28 is equal to 9a plus minus 9a minus 1a plus 33 minus 11. And I get 28 is equal to minus a plus 23. Fair enough, and I'm just going to get rid of my other stuff now. Which means minus a is equal to 9, which means a is equal to minus 9. Now that I have a, and I know what a is, I can now go back to a and put it in there. What's minus 3 times minus 9? It's 20 plus 27. What's 11 plus 27? b is equal to 38. Now that I have b and a, what's minus 9? It's plus 9. Minus 38. Oh, looks like I got the c wrong. Or I might have some of my calculations wrong. In any case, these are steps that you can now complete a, b, and c. Now, according to this, my c is minus 1920 minus 19, which I don't believe is correct. So I probably made an error somewhere along the way. But this technique does work, and I should go back and make sure what I came up with. So far, this is right, and it's just plugging it into this last one that I'd have to make sure of. Sort of looks right. But this is how you discover your A, B, C. Let's see if it's, maybe I did get it right. Let's just see. So according to this, my A is minus 9. Oh, and this is even worse. It's minus 29. I don't buy that c is minus 29. So according to this, y is equal to minus 9x squared plus, what was my b? B is equal to 38. I don't think that's true. Let's see if I got my b calculation wrong. Minus 3 times minus 9. Yeah, I don't buy that. Plus 38x. And according to this, my c is minus 19. Minus 29. Yeah, I'm not sure I buy any of that. And then if I table that, and I just put it for 1, 2, 3, 4, 5. Yeah, I'm going the wrong way. So my 9 should never come out as minus, as a minus. And so I'd have to go back and do my calculations again. Should be going upwards because this is clearly going up. So I've made an arithmetic error probably in the third one. So let's just do the third one again because I'm pretty sure I got the other two correct. The blue formula should be, oh, I know what I did. I didn't put in the correct y value. It should be 28 is equal, yeah, 9a plus 3b, and instead of c, it should be minus a minus b, and the 3b should be replaced with 11 minus 3a, and the b over here should be replaced with 11 minus 3a, and that's where I made my mistake, I think. So you get 9a plus 33 minus 9a, yeah, that's where I made my mistake, minus a minus 11 plus 3a. It's that plus 3a I forgot. So I get 28 is equal to 2a plus 12, no, 22, okay, which means 2a, yeah, there we go, is equal to 6, which means a is equal to 3. So there's my mistake. So that means my a is 3, and that's the formula you're most likely to get it wrong. And if a is 3, 11 minus 9 is b is 2. And if b is 2, c is going to be equal to minus 3 minus 2 is going to be equal to minus 5, which is the number I calculated. So what it should be is positive 3, positive 2, and the number I did indeed calculate 5. And sure enough, those are the numbers we have in the chart. My bad, it's the third equation I got wrong. So if you look at the chart, those are indeed the numbers, and I was able to derive. And also, since it only asked what type of graph function I was dealing with, I can tell you that that was a growth because all the differences were multiplied by 2. And I could tell you that's a parabola because the second differences were the same number, which was 6. So there you go. Determine the zeros for each of the following. So this is just essentially factoring. I'm sorry about that length on that, but it's a good skill to learn how to derive the equation from a chart. Determine the zeros. Okay, this first one is a parabola, so the zeros are going to be where it crosses the x-axis if it does. We're looking for a number that multiplies out to minus 12. How did I get that? Because it's positive 2 times the minus 6, and adds up to minus 1, which means they're very close together, and one is minus and one is positive, and we're of course dealing with minus 4 and positive 3. I like to use what I call slip and slide method, which means I just do it like this, and then I have to take the number that's in front of 2 and divide each of these things by it. Oh, you should always see if you can factor out the 2 first, but you can't. And because this can be divided by 2, I get x minus 2. And because this can't be divided by 2, I slide it in front, and I get 2x plus 3. And if you multiply all this out, you will indeed get that. Now, to figure out the zeros, it's a little bit different. You have to look at the roots. which means the zeros will occur when x is equal to 2 on this one, and when x is equal to negative 3 over 2 on this one, which means the zeros occur at 2 comma 0 and minus 3 over 2 comma 0. So that's where the zeros exist, if they exist. Because remember, a parabola can cross the x-axis twice, or once, or not at all. What about this one? Growth curve. So that one's a little simpler if you know your growth curve, but you just have to understand whether it's been raised or not. So no growth curve ever touches the y-axis unless it's been lowered. And this one's been lowered. So the question is, where does it touch the y-axis? Well, the hint is on this first number. All growth curves have this number. So when x is 0, if this did not have this minus 1 in there, the growth curve when x is 0 would be 1. If I lower everything by 1, it's going to go through origin, and that means it's going to creep down below origin here and shoot up to origin afterwards, which means it goes through 0 there. And you might say, well, how did I figure that out? Well, I had to start with my parent function, know that one of the base points is 0 comma 1, know that when I lower this entire graph by 1, it's going to cross the x-axis there. And since I know it curves down and up, it can only cross once. And that's just knowledge of growth curves. If you take a growth curve, any growth curve, no matter what the base is, if you lower it, you'll see it can only cross once, no matter how much I lower it. And it's got to be lowered any amount. It can be pretty much lowered, you know, a tiny amount, and it'll still cross. See, even there. And let's see where it crosses. If it crosses, usually puts a dot when it's crossing. It should still cross somewhere. Wait. Yeah, I put just too many zeros in it. Let's see if I can. Yeah, 1. Let's see if I just put right there, it crosses. Let's see if I just put one more 0, what happens? Crosses a little further, 1 more 0. 1 more 0. Okay, it's showing where it crosses. Oh, it's that one that really shot it way out. Or maybe I got to zoom in more. In any case, you can see that it indeed does cross no matter how much I subtract. If I subtract a little bit, it's going to cross the x-axis somewhere. And that's just knowledge of your growth curve. What about this one? Well, you have to look at your parent curve. This is a sine curve, and the only thing that has happened is it's shifted left by 45 degrees. Since you know your end, you also have to realize they're only working with the first 380. Since you know your sine curve starts at 0, 0, so there's one crossing on the parent, goes up, crosses again at the halfway point, which is 180, comma 0, goes down, comes up at the 360 point, so 360 comma 0. There's my parent graph. What's happened to this graph? It hasn't been shifted left by 45, it's been shifted right by 45. So we have to go back and say, where's this one over here? Minus 180. So in the first 360 degrees, if I shift everything 45, I'm only going to be using this point and this point, because this point goes beyond 360, and this point here doesn't reach the 360. So that means if I move this point to the right 45 degrees, I'm talking 45 degrees, comma 0, and this point 180, comma 0, if I move it 45 degrees to the right, I'm talking 225, comma 0. So those are my 2 0 points for that function, and again, it comes from knowing what's going on. This one, they're looking at a cos curve, and they're only doing the 30 degrees to the left of the y-axis. They're only doing this 360 degrees, rather. The only thing that's happened here is it's been stretched. So that means it's just going to go up and down and up, but the period's the same, which means the crossing points are the same. So it's going to cross at 0, comma 0. It's going to cross at negative 180, comma 0. And it's going to cross at negative 360, comma 0, which are the 3 points in that range of a cos curve. And if, oh, hang on. I got my zeros wrong. That's a sine curve. So cos curve starts up here, goes down, up, and down. So its first crossing point is right here at 0, 1. So that's not a crossing point, but it will still come down to here. So you have to know what this crossing point is. That's 90, 0, and that's 270, 0 over here, which means over here it's minus 90, 0. It comes down, and minus 270, 0. My bad, not a sine curve, only two crossing points, minus 270, 0 and minus 90, 0. The amplitude changed nothing. There's no phase adjustment. There's no compression. Okay, given this, describe how the graph of x is transformed in each of these cases. Okay, that's outside of the f of x, so that's a y compression. So all my y values will be multiplied by half, or y compression by half. This is outside, so I get a y, every y value will be multiplied by 2. And every x value won't be subtracted by 4, they'll be added by 4. So that's a horizontal phase shift to the right by 4, and that's a stretch by a factor of 2. This is outside the f, so I got a y compression or stretch by a factor of 3, and that minus makes a reflection in the x-axis. Nothing happens to the x, and then I've got a phase shift upwards by 7. So the graph moves 7 units up. This, we did that one. This one has a vertical stretch by a factor of 5. It's been vertically shifted down by 2. And it's been horizontally moved to the right by 3. This you have to remember your compound interest formula. And it's fine if you don't. That's just, you're allowed to use Google for these things if you can't remember a formula. And I do remember it, but I'm going to just show you how easy it is to come up with a compound interest formula. Google compound interest. And there's even a calculator if you want. But let's do the formula. So there's the formula. And also always read your question well. Okay, so it's saying invested 1,000. So that means that's my principal. P is equal to 1,000. My rate is 8%, so R is expressed in decimals. That's 0.08. 0.08. Compounded annually, which means my number of times and my number of times here are just 1. You put an n here if it's compounded quarterly, it would be a 4 for n. If it was compounded monthly, you'd put a 12 for n. But because it's just annually, the n doesn't exist. And then it says you'll have after t years, so they want the general formula. So it would be this. A, what was my principal? $1,000. 1 plus 0.08. What's 1 plus 0.08? 1.08 to the power of t. And they didn't give us t. So that answers question 1. A, 5a. And 5b, how much after 3 years? You replace this with a 3. You do exponents first, so 1.8 to the power of 3. To the power of 3. And then you multiply $1,000. So the answer is you will have this much, and it's rounded up. So it's 71. You'll have this much after 3 years at 8%. Pretty good. And then finally, does the amount of money in your account increase at a constant rate each year? No, of course not. This is a growth curve. If you look at t and just call it x, we're talking about a growth curve. So it's going to go up like that, which means its rate of change increases dramatically. And compound interest, the sooner you save and the largest amount you can save, will lead to millionaires. If you wait till you're later in life to start to save, you really don't benefit. The big benefit is youth and saving, and it will just grow skyrocketing with compound interest. The height above the ground of one of these seats at a Ferris wheel in meters can be modeled by this function. So this again, you have to know your parent function and understand what's going on. So a normal function off the ground has an amplitude of 1 and has an axis of 0. We don't, this is not written correctly, so we have to rewrite it correctly as h of t is equal to 7 times sine, and then they're putting it in terms of sine of time. They're multiplying it by 15, and they're adding 8, which means that my entire Ferris wheel is stretched by 7, so the amplitude is now 7 and minus 7, and then raised by 8. So normally the max value here would be 7 and the min value would be minus 7. But when I add 8 to it, my max value is now 15 and my min value is now 1, which means I'm dealing with a Ferris wheel that is 15 meters off the ground at the top and 1 meter off the ground at the bottom. Where t is measured in seconds. What is the maximum min heights it reached in any seat? Just did it. And that's when you figure out the amplitude first and then you do the adjustment upwards. How long does one seat on the ride take to rotate back to its starting point? Well, that's a period thing, and that's affected here. What's the normal period for a circle? It's 360. Now, 15, you might say, is 15 times 360, except x values do the opposite. So I'm going to be dividing by 1/15th, 360 degrees, and my result's going to be in time, seconds. I believe seconds, if it says seconds. Yeah, measured in seconds. So really, 360 times 1/15th is 360 divided by 15. So 360 divided by 15. And we discover it takes 24 seconds for this Ferris wheel to go around. 24 seconds is now the new period. Period's always affected by the multiplier in front of the x or whatever thing we're measuring in the middle. And after 30 seconds, what will the height be? That's a very good question. After 30 seconds, what will the height be? Well, for that, you need your original equation. And they're saying 30 seconds, right? So they're putting an exact amount in for 30 seconds. So you're going to do 7 times sine. And what's 30 times 15? It's 10. It is 450. What's the sine of 350? And then you got to add 8. So you got to take the sine of 350 first, and then multiply by 7, and then add 8. So sine of 350, or 450 rather. And actually, that might not be the best thing, but we'll see. Trig sine. Yeah, so that does not make sense to me, so I don't think I did it correctly. 30 seconds, because the ride is 26, I think I discovered. 360 divided by 15. Yeah, so at 24, it'll be down at the bottom. So let's see. Well, might work. Yeah, 6 seconds. So every 6 seconds, it's going around a quarter. So yeah, that does make sense. So sine of 450 is 1. 1 times 7 is 7. And 8 is, plus 8 is 15. Now, does that work? Does she enter at the top? She enters at the top, at the bottom rather. Oh no, she enters at the middle point, because sines start here and then go down. So she enters at the middle point, which means at 6 seconds she'll be at the peak, which makes sense that this comes out at the peak. What will her height be? She'll be at the maximum. And if you want to see logically where that makes sense, it's easy to think that people are getting on at the bottom. But when you look at a sine curve, it's not phase shifted, starts here, goes up to the peak, comes back down, goes back down to the bottom. This part here, if it's on a Ferris wheel, is getting on right in the middle. Since the ride is one full cycle is 24 seconds, and how much is 24 divided by 6? It's quarters. That means every 6 seconds it hits top, middle, bottom, and start again. Since 30 seconds is 4 seconds after one complete 24-second ride, it makes sense that it'll be at the top, which is 15. And that holds true for our formula, which is 7 times the sine of 450, 15 times 30, plus 8. Sine of 450 is 1. And you might say, why is sine 450 of 1? Well, what's 450 minus 360? It is 150, 190. No, it's 90. So you can see that 450 is the same as 90 degrees. Sine of 90 is 1. And times 7 is 7, plus 8, rather, is 15. So it works in the formula as well. And you might say, why didn't I divide by 15 in here? No, that's only when you're trying to figure out the period. When you're actually using the formula, you use the exact numbers that are in the formula. Create a chart to show rates of change in linear, non-linear. Yeah, well, we could do that, but I've kind of demonstrated it well. Okay, I'm going to stop. That's intro to chapter 2.